Okay, so we're still in 10.5. I know I said it would be 2 videos, but it came out to be 3. I'm trying to keep the videos somewhat relatively short, like below 10 minutes or so. There's still one more thing we need to talk about here in this section, and that is something called the root test. So this is a theorem. The ratio test that we saw previously in this section was very powerful, probably the most powerful thing out there. But it doesn't quite work for everything, and there's a couple of examples where the root test is actually a little bit better and easier to work with. So just a definition for the root test, let there be some series, these a sub n values, um, be any series, oops, and also suppose that we have the following. So here's the root test part of it. So we're still going to be looking at this limit. This is the limit again as n goes to infinity, but we're not looking at the ratio of consecutive terms anymore. For the nth root test, we're going to be looking at the nth root of the absolute value of the nth term of the series. If this does approach some number, we're still going to call it t, then again, there's a few different things that we could say. The first thing, and these should actually match from the ratio test. The series converges absolutely if my t is less than 1. The series is going to diverge if the t is greater than 1 or if t is infinite again. It's spelled just as good on here as I do in class. And the test is going to be inconclusive if my t comes out to be equal to 1. Okay, so we're just going to jump straight into some examples for this one. Let's look at this example. This should also kind of show you when to use the root test and when to use the ratio test. So our first example, we're looking at the series as n goes from 1 to infinity of n squared divided by 2 to the n. And we want to know, does this converge? Okay. So, if this was a test question, you would just go through all of your different tests. The nth term test would tell you nothing. It would be inconclusive. You could try integrating this, but it would be very, very, very difficult. You could do the ratio test for this one. It would work. But whenever you have something to the n power, sometimes the root test is a little bit easier to do just because taking the nth root of something to the n power is going to cancel out and turn out to be very nice. So let's just try it and let's do it. So here, we're just going to look at the nth root part and we'll take the limit of it after the fact. So here we're going to be doing the nth root of, and make sure you do the absolute value. It is pretty important here. I think just copying down the nth term. So that n squared divided by 2 to the n. Okay. We can drop the absolute value at this point because these are all positive terms as the n goes from 1 to infinity. And then whenever you're taking the root of something, you can just take the root of the top and the bottom separately, which is what we're going to do here. So let me write this as a fraction. And then we're going to take the nth root of n squared. And then we're also going to take the nth root. I'll go ahead and write it out here. The nth root of 2 to the n. Okay. We'll worry about the numerator here in a second, but I hope you can at least see that the denominator is just going to come out to be 2, because that nth root and that 2 to the n, the exponent and n are going to cancel each other out here. Now for this, we're going to be using some of the properties that we've seen back in algebra when it comes to roots and exponents. We're just going to rewrite this a little bit as the nth root of n all squared. So this is just interchanging the two exponents with the root and then with the exponent of the power. Okay, so remember that we're taking this as the limit as n goes to infinity. So we're taking here the limit as n goes to infinity. This term up top is actually something that we saw back in section 1. This is one of those common sequences that we know the answer to. As n goes to infinity, this just approaches 1. And because that just approaches 1, that says that this, as the limit of n goes to infinity, is just going to approach 1/2. Don't forget that that is my p-value. And since the p is less than 1, then that says that my series above doesn't just converge, it converges absolutely. Okay, great. So that's just an example of using the root test here. And I got one more example. So it's pretty similar, but just to get a little bit more practice here, so we're taking the limit as n goes from 1 to infinity of 2 to the n divided by n cubed. And I wanted to know, does this converge? All right, so again, because we have that n as an exponent here, the root test may actually be a little bit easier, so we're going to do the root test here. So we have to take the limit as n goes to infinity of the nth root of the absolute value of the nth term. So let's not worry about the limit yet, let's just go ahead and look at that, the nth root. Okay, so the nth root of the absolute value of 2 to the n divided by n cubed. I didn't have to write the absolute value here because I already know that these terms are all positive. We're going to do the same thing here. We're going to take the nth root of the numerator and the nth root of the denominator. And I hope you can kind of just visualize what's going to happen here. So the nth root of the numerator, the n's just cancel out. We're just going to get that base of 2. For the denominator, I'm going to take the nth root of n cubed, and that's going to be the same thing that happened in the previous example. I'm going to bring that nth root on the inside, so it's going to be the nth root of n all cubed, but that just comes out to be 1 cubed, so just 1. So that means that my p-value comes out to be 2. And remember that when the p-value is bigger than 1, the series diverges. Okay, so that concludes 10.5. If you have any questions from the homework, just let me know, and I'll make another video kind of doing some of the more complicated problems from the homework.